Earlier in the course, when we first were talking about limits, we came up with a lot of tricks for evaluating limits, but I was actually very careful to only show you the kinds of limits that we could actually come up with nice algebraic tools to compute. In fact, there are a lot of limits that are just too difficult to compute with plain old algebraic tools. Here's an example. So suppose we wanted to find the limit as x goes to 0 of x squared over 1 minus cosine x. Well, if you try to use the plugging in the number idea of evaluating a limit, in the numerator you're going to get 0 squared, and in the denominator you'll get 1 minus cosine of 0. Well, this is 0 over 0, right? Cosine of 0 is 1, so your denominator is 0. You get 0 over 0, and remember 0 over 0 doesn't really, that's not a number. All that is trying to tell us is that we need to try harder. Right? 0 over 0 isn't any kind of answer. Depending on how this 0 over 0 comes up, this might be infinity, it might be 0, it might be some finite number, this limit might not exist. Right? 0 over 0 doesn't actually tell you anything other than you need to try some other trick. But because of the fact that there's cosine in here, there really isn't any obvious trick to try. I mean, you might mess around with trig identities for a while, I guess, but I don't think there's really anything productive to be done here. So maybe what we should do is sort of abstract away from this particular example to see what are the features of this example that are causing the problem. And here's one way to do that. So we ended up with 0 over 0. By the way, this sort of expression that doesn't really mean anything, it could, depending on how it comes up, it could mean a lot of things. This is called an indeterminate form. And there are several, but 0 over 0 is a big one. Infinity over infinity is another common indeterminate form, but we will see others. So the situation that caused the problem was we were finding a limit at some value, and our limit was a quotient of two functions, and the limit of the function on the top was 0, and the limit of the function on the bottom was also 0. Well, in this case, we can sort of unsimplify this expression to give us a little bit more to work with. The problem with the way it's written now is it's just sort of, it's so simple that there isn't anything obvious to try. But one way to deal with that kind of situation is to kind of unsimplify things so that you have just more stuff, more pieces lying around to do work with. Let's make an additional assumption that f and g are continuous at a, at x equals a. If f and g are continuous at a, then that means that not only is the limit of f 0, but f of a is actually also 0, because if f is continuous, that means that the limit is equal to f of a. And then same thing for g of a. All right, well, the reason that we can use this to kind of unsimplify this limit expression is because it lets us write f of x minus f of a over g of x minus g of a. Right, f of a is really 0 and g of a is really 0, so having these extra pieces here doesn't hurt, because after all they're just 0. But now that we have them both there, this is starting to look a little suspicious, because this numerator, it looks as if it's trying to be part of a difference quotient, right? F of x minus f of a over x minus a. It looks like it's trying to be this. The only thing that's missing is the denominator. There's no over x minus a. And actually the same thing is happening in the denominator. It looks like this is, the denominator here is trying to be a difference quotient involving g, except there's no x over x minus a down there. Well, we can have the over x minus a if we want it in the numerator, right? Like this. But the price that we have to pay is that we also have to do the same thing in the denominator, like this, right? If you multiply by something in the numerator of a fraction, you have to do the same thing in the denominator. But that's okay because we wanted this x minus a to show up in the denominator anyway. So this gives us the limit as x goes to a of f of x minus f of a over x minus a over g of x minus g of a over x minus a. Well, this, now that we have this split up this way, it's actually safe to take the limit of the numerator and the denominator separately, right? That's what we couldn't do before because we just ended up with 0 divided by 0. But now if we take the limit of the numerator and denominator separately, we get the limit as x goes to a of f of x minus f of a over x minus a over the limit as x goes to a of f of, sorry, not f, it's g down here, g of x minus g of a over x minus a. And this numerator, well, that's just the derivative of f at a. And same thing for the denominator, that's just the derivative of g at a. Well, this calculation kind of assumes that these derivatives exist, and it's not really exactly clear what would happen if these derivatives didn't exist, but so there's a little bit of a question mark here. And actually, I've snuck in a couple other assumptions. So I did add this assumption that f of a is 0 and g of a is 0. And actually, there's another hidden assumption in here, which is that f and g don't, so we see that they're going to 0 as x goes to 0, but we're sort of also assuming that they don't cross 0 infinitely many times as x goes to a. But it turns out that all of these issues, all of these extra little assumptions that I made, can actually be removed if, and the result is, instead of this quotient of derivatives, what you get is the limit as x goes to a of f prime of x over g prime of x. Now this should seem plausible because if f and g are both well behaved and they have continuous derivatives, then this quotient of derivatives, f prime of a over g prime of a, will be equal to the limit as x goes to a of f prime of x over g prime of x. So this maybe shouldn't be so surprising. So what we found here, well, we haven't found this. I've sort of hopefully given you some idea of why this is plausible. This is not a proof. If you do want to see a complete proof of this fact, you can Google it. Wikipedia has a fine proof. But what the fact that we're getting at here is if you want to know a limit like this, where you're getting 0 over 0, and the limit of the numerator is 0, and the limit of the denominator is 0, then, so these things imply that the limit that we want, the limit as x goes to a of f of x over g of x, is equal to the limit as x goes to a of f prime of x over g prime of x. Now it's important to realize that we aren't using the quotient rule here, right? This is a totally different thing. We aren't trying to calculate a derivative. Instead, we're trying to calculate this limit. And to calculate this limit, we will in fact take derivatives of the numerator and denominator. But notice that the numerator we end up with here is just the derivative of the numerator of what we started with, and then same for the denominator. So this is not the quotient rule. Do not confuse this with the quotient rule. This fact about limits, that if you're getting 0 over 0, you can replace your limit with the derivative of the numerator and denominator. This fact is called L'Hopital's rule. Not after the person who discovered it, I think, but after the moneyed patron of the person who discovered it. Sometimes you'll see L'Hopital spelled like this, and sometimes you'll see it spelled with a circumflex over the O like this. Kind of depending on what era the person writing is in. So again, the idea is if you end up with this indeterminate form, 0 over 0, then you can just replace the numerator with its derivative, replace the denominator with its derivative, and take the limit of that resulting thing instead. So let's see how this works in an example, a couple examples. So let's find the limit as x goes to pi of sine of 4x over tangent 5x. Well, the first thing to do is just check what happens if x, let's just check directly what happens if x goes to pi. In other words, just by plugging in pi. Because the numerator and denominator are both continuous, we can calculate the limit of the numerator and denominator separately as x goes to pi just by plugging in the pi. So now if we don't get an indeterminate form, then this expression would be the value of the limit just by plugging in pi. But we are going to get an indeterminate form. In the numerator, we get sine of 4 pi. In the denominator, we get tangent of 5 pi. But that's 0 over 0. That's indeterminate form. That's an indeterminate form. But because we're getting this 0 over 0, that's exactly the situation where L'Hopital's rule applies. So we can replace this limit, the one that we were calculating, with the limit as x goes to pi of the derivative of sine of 4x divided by the derivative of tangent 5x. Okay, so that's going to be the limit as x goes to pi. Now this numerator, derivative of the numerator, that's going to be cosine 4x, and then the chain rule is going to spit out a factor of 4 here. And then in the denominator, derivative of tangent is secant squared 5x times the derivative of the inside, so that's going to be 5. All right, and now we can take the limit of this as x goes to pi. Well, here we have to start all over again, attempting to evaluate this limit. So maybe the first thing we should check is this function we're taking a limit of, the whole thing, is it continuous at pi? Well, almost every function that we write down is continuous everywhere it's defined. Certainly quotients of trig functions are continuous wherever they are defined. And these are defined at pi. So by continuity, we can just plug in pi. So we're going to get cosine of 4 pi times 4 over secant squared of 5 pi times 5. Let's see, cosine of 4 pi, that's 1. So in the numerator, we just get 4. In the denominator, secant of 5 pi, secant squared of 5 pi. So I think secant 5 pi is minus 1, but then square that and you get a plus 1. So 1 times 5, that's 5. So this limit is 4 over 5. And, you know, without using L'Hopital's rule, I'm not so sure how you would calculate this limit. So it's really handy to have L'Hopital's rule. To see how useful L'Hopital's rule can be, let's come back to the example that made us think about it in the first place, which is this one, the limit as x goes to 0 of x squared over 1 minus cosine x. So again, let's just check if we get an indeterminate form. Remember, we're just going to sort of evaluate this limit the naive way by just plugging in 0. In the numerator, we get 0. In the denominator, we get 1 minus cosine of 0, but cosine of 0 is 1. So we get 0 over 0. So that's our indeterminate form, 0 over 0. So we can use L'Hopital's rule. So by L'Hopital's rule, so this little decoration on an equals is my way of saying that I'm using L'Hopital's rule here. So by L'Hopital's rule, we can replace this limit with, so the derivative of the numerator, so that's 2x, and in the denominator, take the derivative of the old denominator. And that's going to be, looks like sine x. All right, and now we can try to evaluate this limit. Well, if we evaluate this limit, again in the naive way by just plugging in 0, we get 0 over 0 again. So this is still an indeterminate form. So what should we do? Well, since it's still an indeterminate form, we could try using L'Hopital's rule again. Now, there's no guarantee that using L'Hopital's rule a second time will help, but it's a possibility, right? It's something to try. So it is possible that using L'Hopital's rule multiple times just gets you into a loop that never actually produces a value for the limit. But in this example, if we do one more trip through L'Hopital's rule, in the numerator, the derivative of 2x, that's 2. And in the denominator, the derivative of sine, that's cosine. And now if we take the limit directly, just by plugging in 0, we get 2 over 1, and that is defined. That's 2. So this limit is actually 2.